Welcome to Physical Attacks and Countermeasures, the second session, which is Introduction. What you learned today, technically in this lecture, is very much basics, cryptography and cryptographic devices, and super simple example of attacks on physical devices, and the formal definition of physical attacks, and also a bit basics of the hardware design. I guess most of you learned that the cryptography is the science of writing in secret, which is too simple, of course, no? And you can also say that it's the scientific study of techniques for securing digital information, transactions, and also the computations. Usually, four requirements are necessary. Integrity, confidentiality, authenticity, and non-repudiation. If you don't know their meaning, integrity means that if there are two parties that they communicate with each other, you need integrity means that the party which receives the data should understand, should find out that something changed during the communication. And the confidentiality means that somebody who is in this communication and listens to the communication should not understand anything about what you are transferring. And authenticity, you should be able, the receiver should be able to find out who is the sender, or the sender should be able to prove that, okay, I was that one who sent this. And non-repudiation is the other way around. It means that you sign something and then you cannot say, hey, I was not that guy who signed it. This is in a simple words. And usually cryptographic primitives either are able to fulfill one of them or a couple of them. And for every need, we may use different kind of cryptographic primitives. Classical scenario, definitely you have seen this, that two bodies want to communicate, and then of course the communication link is not secure, and then you need to use a cryptographic scheme here, and if somebody in between can understand and can listen, this is the meaning of the confidentiality, and this is what we mainly deal in this lecture. It means that we mainly deal with confidentiality. For example, you use the AES, or symmetric cryptographic algorithm. Means that the key at both sides should be the same. That, for example, this guy encrypts the message with a key, and the same key should be also with the other side at Alice, and then should be able to decrypt this. And then we mainly deal with secrecy of this key. And what is important in this principle that you may have heard, that a crypto system must not be required to be secret. And it must be able to fall into the hands of the enemy without any inconvenience. Means that if you design something, as a cryptographer, you design something in a cryptographic algorithm and say, hey, this is secure, but I don't actually say to you what are the details of this cryptographic algorithm, or I build a device that the two bodies are communicating with each other, and you say, I use a cryptographic algorithm and it's super secure, I don't tell you what it is. This is actually not the case. This is not what is recommended, and actually this is not what is acceptable in the community. You should be able to say what exactly is this, the cryptographic algorithm, how this process is done. The only security that you have is the secrecy of the key. It means that only the key should be secret. Not the algorithm. As I said, the security of the crypto system is based on the secrecy of the key, and it of course makes the things much simpler. It's easier to keep a secret key secret, to provide the secrecy of the key instead of providing the secrecy of the algorithm. And then everybody knows what the algorithm is, for example, the AES. And then you just keep the key secret. And then at any point in time, you can also change the key. If by any chance you have problem and say the key may leaked somewhere, and then I want to change the key, or you define just session keys. Repeatedly you change the key if you are afraid that the key is leaked somewhere. And the communication with many parties also become easier. And you can also publish your design. Not design, I'm not necessarily the cryptographic implementation, actually the cryptographic scheme can also be published, and then it goes to the public review. Yeah, and this is super important. For example, you may have heard about the AES, as I said a couple of times. I mean, this is an algorithm which is standardized by NIST, NIST, National Institute of Standard Technology in the US, in America. But actually they have not designed this. Yeah? I mean, some other guys through a competition designed a couple of algorithms. They submitted their algorithm and it went through the public review, and some other researchers checked this, and finally one of the submitted algorithms has been selected as the advanced encryption standard, or let's say AES. Yeah? And at the moment still research is going on the AES. Still there is a high interest to still examine and evaluate the security of the AES, and the research still is going on. It's a public, let's say, review. Yeah? And as if you do not publish your design or cryptographic algorithm, you are not actually aware of all the security flaws. Yeah? You may not. There are a couple of examples of this. Yeah? I mean, the companies design algorithms and then they use it in their product. They didn't tell anybody, or kept it secret through or protected through the NDAs, non-disclosure agreements. And then nobody actually could do a public review, or if they found any mistakes or a security flaw, they could not publish it till the algorithm somehow leaked somewhere. Yeah? And then some other researchers who were more expert in that area, they published then the flaws of the algorithms, which were used by some companies. There are a few examples that I don't want to name. Yeah? But what is important, the definition of the security, is that a cryptographic scheme for a given task is secure if no adversary of a specific power can achieve a specific break. Yeah? You cannot make a cryptographic algorithm or a scheme or primitive and say, this is secure, and I don't define the adversary model. Yeah? You have to define the adversary model and say, under this adversary model, I can say that my cryptographic primitive is secure. For example, you may say AES is secure, but why AES is secure? Yeah? I mean, under which adversary model it is secure. For example, AES, the simplest version of the AES, 128 bit of the key is used. Yeah? You may say, I search through all possible keys, yeah, which is 2 to the 128. If the adversary has that power, then the algorithm is not secure. Yeah? But then we calculate and say, the adversary is not able to search in a space larger than 2 to the, for example, 90 bits, yeah? Let's say. At the moment, with the current devices that we have, with the current PCs which are available in the entire world and so on. Yeah, I mean, let's suppose that in 2 to the 90 space or 90 bit can be searched. Yeah, then you say, if the adversary model is this, I mean, the cap is for the 2 to the 90, then there is no possible attack on the AES. Yeah? Then you have to define the adversary model. This is exactly the same in physical attacks. So we will learn later. We have to define the adversary model and say what are the possibilities and abilities of the adversary. Otherwise, you are not able to prove the security, yeah? Or claim any security. Now, what are the cryptographic devices? Yeah? Cryptographic devices are electronic devices that implement cryptographic algorithms and also store cryptographic keys. Yeah? For example, your mobile phones. There is a microprocessor inside. There are a couple of crypto coprocessors inside, like the AES, like the might be the RSA, might be elliptic cryptography, and so on. Yeah? And these are the cryptographic devices. Or very simply, you may have seen garage door openers. Yeah? You press a button, the door opens. You press the button, the door closes. Or the key fob of the car. There is a button, then you press the button, and then the central lock of the car opens and also closes. All of them should have cryptographic primitives, yeah? Because these communications should be secure. Otherwise, anybody who is listening to this communication can also open or close the door of your car. Yeah? Then, what is important is that that these devices which implement a cryptographic algorithm, they are actually called cryptographic devices, yeah, and they should also fulfill some other security requirements, yeah, that we will learn in this lecture. Good. And the thing is here, exactly like the principle that we have seen, their security should also not rely on the secrecy of its implementation. For example, you say, hey, I have implemented the AES, but I don't know how I implement it, yeah, but it's secure. You cannot attack it. You cannot recover the key of my implementation. Yeah? This is also, again, not possible and not acceptable in scientific community because it's actually known as security by obscurity. Yeah? Because we are not actually accepting this. I mean, because as I explained, or gave you one example, this implementation that you try to actually say is obscure, then what you do, you give it to some engineers who are expert in reverse engineering, and they find out how exactly the implementation is done. And afterwards, they can do the analysis easier. Means that if even you have some protection against physical attacks, some companies still do some obscurity. Why? Because they try to make the reverse engineering harder. Means that you have one more step into the task that the attackers have to do or has to do. Means that the attacker has to first do the reverse engineering and overcome this obscurity to understand how the implementation is done, and then try to perform some kind of physical attacks that we learn in this lecture. Yeah, and then breaking a cryptographic implementation or cryptographic device doesn't mean that we break the cryptographic algorithm. For example, the AES is implemented in your key car, the key fob of your car, and then you break it by some schemes that we learn in this lecture. Yeah? But it doesn't mean that you broke the AES. No? You broke one implementation of the AES. It means that you recovered the key which is used in this algorithm, in this implementation. Yeah? And as I said, if the key is going to change frequently, then you just found one of them, yeah? And it's only valid for the duration that the key is valid. And as I said, the security of cryptographic primitives are just based on the secrecy of the key. Yeah? Once you recover the key, the security is fully gone. Yeah? And then what we do, or physical attacks, we try to recover the key which is stored inside the cryptographic device or is used for the cryptographic operations. I mean, sometimes the key is not stored at all. And sometimes you just recover the key without dealing with the cryptographic primitive. Sometimes you do not care about how it's saved or where it's saved, but you just check or try to understand or recover the key when the key is actually used in the computation. Some examples. Yeah? I have to say that this topic, physical attacks, came to the scientific community by one super old example which is not valid anymore. You know? The pay TV systems. I guess most of you are younger to actually have seen this, but many years ago, if you wanted to have satellite receiver and then there were some channels that you want to watch, and then you had to put a smart card inside to be able to watch particular channels, and you had to pay for that. I mean, get some subscriptions to be able to de-scramble these channels and watch them. Yeah? At the moment that the business model is completely different because every device has an internet and so on, and it's not valid anymore. But many years ago, then many companies were actually selling these cards. Yeah? And these cards are actually similar to the ETC card that you have, the banking card that you have. There is a chip inside, and there are some pins that this actually card goes in, and then this is nothing else than a microcontroller. And then it communicates with the device, with the receiver, via a particular protocol. Yeah, and then of course there were very much interest in hacking community to hack them and to understand how this works, and then make a copy and then sell these illegal copies, or put them in the internet and everybody could buy some other cards which are the actually empty cards, plain cards that you could program, and then you could actually get some algorithms and put it here even without having knowledge of doing any reverse engineering. Just the binary file were available on internet and people put it there and then try to watch the scrambled channels, yeah, illegally, of course. And then the topic of physical attacks came via this business model. Means that by just copying the things, I mean the thing didn't work, yeah, copying the binary, or let's say fully getting how this communication works here. But then the cryptographic algorithm were inside, and then also the session keys, means that the key was also changing, and then finding out what is the key. Then, for example, the AES is used between here, this guy, and also the receiver, and then there was a key inside, and then performing some attacks to find out what the key is, and then make an illegal copy of the card again was the business model. Yeah? And one of the examples of the physical attacks came to the market, and then afterwards became one of the scientific fields in cryptographic implementation, or let's say cryptographic engineering. Nowadays, this business model is not valid anymore, but there are many other things that the physical attacks are still applicable. And I have to say, during the last 20 years, many devices that are actually are used by normal users, they have protection against these kind of attacks. I mean, this is something that was not there 20 years ago. For example, most of you have heard about the BSI, BSI or BSE in Germany. They define some criteria. For example, the banking card, the EC card that you are using, they should pass some security requirements, and these security requirements are defined by BSI. And then there are evaluation labs that they are actually certified also by BSI, that they are able to examine or evaluate the banking cards. For example, you are a company who produces this banking card, and you want to sell this banking card to a bank, and the bank buys them from you, and then sell it to or give it to the customers of the bank. And these cards have to go through the evaluation lab, and they should get a certification. The certification should be also validated by BSI to be able to be sold in Germany. Means that all of the EC Karte that you have actually are certified. At least their design has been certified by BSI. Of course, first through the evaluation labs, and then certified by BSI. And this is something which was not like this 20 years ago. I mean, many things has been changed, and the knowledge is also at a higher level, and researchers learned what to do, and the industry also learned what are the threats and how to provide security against them. And these attacks actually are those that we are learning in this lecture. There are many examples of this electronic money, like the EC card, ID cards, passport. I mean, all of your passports and ID cards, the Ausweis that you have, I mean, all of them have also the cryptographic primitives, and they should also provide security against this kind of attacks. I explained that car remote controls, immobilizers. I don't know whether you know the immobilizers. I mean, inside the key of your car, there is another chip which communicates wirelessly with the ECU of the car. Means that if you just make a copy, mechanical copy of the key, if your car has a mechanical key, you may open the door of the car, but you are not able to turn the motor on. Because there is a chip inside the key fob which communicates wirelessly to say I'm a valid actually key fob, and this is called immobilizer. Even if you make a mechanical copy of the key, then you can open the door, but you cannot actually drive the car. USB tokens, not all of them. I mean, USB sticks that you have usually don't have any cryptographic primitives inside, or there are not cryptographic devices, but there are USB tokens that they are secure. I mean, you set a password, and they should also some kind of protection if they are not fully based on software. You may have heard about the RFID tags. For example, the devices or the cards that you pay in Mensa here, in food canteen. Then this wireless communication should be also secured, and for that, definitely there are cryptographic primitives inside the card. And this card, some of you may know it, that the card is actually communicates in a wireless way, but how? There is still the same chip like the EC card. There is a chip a smart card, but the power of this chip is provided by the antenna. Means there is an antenna inside the car which receives the energy via the field when the card is closer to the reader, and then what happens? It receives the card and then it communicates through the wireless channel. And this chip inside the card, which has also the antenna, is exactly one cryptographic device. So it's a microcontroller with some cryptographic coprocessors. There are many other cryptographic devices that are involved in their daily life. For example, your laptop, your mobile phone, many other things that you may not think of. And of course, there is a huge interest to break them, sometimes for fun, sometimes for financial gains, sometimes for illegal copying and so on. I mean, of course, it's becoming harder and harder to break them because protectionist schemes are implemented and these devices are becoming smaller and smaller with respect to technology, and it's harder to manipulate them, but there is always an interest to manipulate them or break them. Good. What are the attack scenarios and the goals? The attacker this is our assumption at the first stage is a legitimate owner of the device. Means the attacker can do anything with the device. The attacker can show that she is or he is the honest owner, and also can manipulate, disturb, and also fully observe the behavior of the device. Means that we do not put any limitations first on the attacker. Means that you have your own card, your Ausweis, ID card, and then you do whatever you want with it. I mean, nobody stops you. Of course, you may break it, and then you may order a new one, and you pay for that. But nobody stops you if you want to manipulate that. And then the goal of the attack or physical attack is to find the secret key, which is stored inside or is just used by the device. And as I said, once the key is revealed, then the security is fully gone. And then afterwards, the attacker can may be able to do some deciphering the communication of the other devices, or counterfeiting the content, or illegal access to some secured objects. For example, you rent a car. You get the key fob, and then you bring it to the lab, and then you perform some physical attacks. You recover the key, make a copy of the key fob. You give the car back to the car renting company, and then afterwards still you can access the car. I mean, you may not be able to drive the car, but still you can open and close the door of the car. This is a very simple scenario, which is still valid. If you're able to do that, then this still is valid. It's one example. Physical attacks means to use the physical properties of cryptographic device in order to break it. And then for that, because you need to observe or use the physical properties of the device, and you need to have physical access to the device. Most of the time, as I said, attacker should be a legitimate owner of the device, and then should have a physical access. Of course, there are some other examples that the attacks are also possible in a remote way. Means that even you are able to perform some attacks in the cloud. Even you are able to communicate with a server, and then based on the delay of the communication, how long does it take for the server to respond to you, then you may also recover some secret from the server. But most of the time, or the things that we do in the lecture, we assume that we have physical access to the device. Then we have started with an example, which is a silly example, but this is just to give you then information how this works. I mean, this is not a cryptographic device that you will see now. I mean, this is just to tell you how the physical attacks may work. Somebody finds a USB stick with a secret data on it, and then assume that, and then the USB stick has an 8-digit PIN. It means that you should enter the 8-digit PIN either on the program or on the USB stick by itself to get access to the content. And then if you want to check all of these 8-digit PIN, and of course there is a delay. I mean, if you're super fast with some devices, then still, if we assume that checking every PIN takes 1 second, and we assume that the device doesn't lock after 10 times you enter a wrong password or wrong pin, even if we assume that, this is exactly the point that I said, be open-minded. I mean, you should be open-minded at the moment. To say this is not a valid attack, but assume that this device exists like this. Then checking 10 to the 8 possible pins takes an ages. I mean, 3 years are required, and of course, this might be the data which is on the USB stick already outdated and not of any of our interest. And then the physical attack or physical attacks may help the attacker to overcome this 3-year delay. How? Suppose that the attacker knows the implementation platform, how the implementation is done. For example, there is a microprocessor which checks this 8-digit pin. And it's, of course, when it's a processor, then there is a software which checks this pin. And then checking usually, I mean, if you are a software engineer or if you write a program, you want to check that the 8-digit pin which is given by the user is the same as the one which is saved inside. How you check it, of course, digit by digit you check. You may use some kind of modules or algorithms or functions like the strcomp or memcomp if you don't want to check byte by byte or digit by digit, and you know how this works. Once the wrong digit is detected, the function terminates. There is a loop. For example, strcomp of, for example, S1 and S2, or even if it's memcomp, it's not str, for example, this mem. And what you do, there is a for loop. I mean, I just write here the pseudocode. I mean, we are not writing any C code. For I, for example, equals 1 till 8. And then you say if S1 of I is not the same as S2 of I, then what you do, for example, you return false. This is the end of the if, and this is the end of the for. And if it didn't return, then what you do, you return true. This is a simple thing that you may do. Then what happens, if the first digit is wrong, it returns directly. If the first digit is correct, but the second digit is wrong, then it goes one more time through the loop and then returns false. Means that the time which takes to answer you depends on the number of digits which are correct. If the first digit is wrong, then it takes shorter. When the first digit is correct and the second digit is wrong, then it takes a bit longer. This is what we can do, means that what we can measure. And this is our assumption that we are able to measure the time from the time that you enter the digit, the time that you enter the pin and the way that it's checked. Then how we can measure this time? I mean, if you're a bit, you know a bit of the electrical engineering, you may have a counter to count very fast because the clock of this microprocessor might be super fast, and then you need to measure it. And then sometimes the clock of your counter to measure this time is not as fast as the clock of the microprocessor, and then you may have some actually noise in your measurements and so on. But if we are able to measure this and say that, okay, the time which is, or the execution time depends on the data, which we call it data dependent execution time, then the question is how the attack works. This is our assumption. The attacker is able to measure the time from sending the pin and to get the response. And then the attacker selects a pin, completely random or arbitrary pin, and only change the first digit. And for each one, the attacker measures the time. I mean, you just select an arbitrary pin, for example, all of them 0, and then change the first digit, 0, 1, 2 till 9 for the first digit, and then measure the time, and then the longest time should actually show the correct first digit. This is simple. Of course, it might be super noisy, and then you need to measure it many more times and then get average. Yeah? For example, you send all 0, you get average, you send 1 and the rest 0, and then you get average a couple of times, and so on. Yeah? And then finally, the first one, the attacker can do the same for the rest. Then you measure first for 0, 0, everything 0, and then for 1, 0, and then for 2, everything 0, and then 3 till 9, 0, everything 0. And then I also measure the time of this. I would say this is T0, this is T1 till T9. And then if it was noisy, then again measure this, for example, T0 couple of times here, and then get average, or I give this one and measure the time many times and then get average to have the T9. Yeah? And then the maximum of this, I plot them and then look, see one of them is much higher than the others and say, okay, this one was, for example, the correct one, means that the first digit I found. And then I repeat this with the other digits. Yeah? Then what I say, then I change this, yeah, in a way that 3 is the correct one. Then I remove everything here, yeah, and repeat this by fixing the first digit to 3. Yeah, means that here 3, 0, 3, 1, 3, 2, 3, 3 till 3, 9, and I repeat the same. Then I find again the second digit, and so on. Yeah, this is a divide and conquer fashion. Yeah, and divide and conquer actually helps us in physical attacks. Means that you are not searching for the correct pin or 8-digit pin in whole, but you try to find each of them individually or one after each other. And this is exactly why physical attacks work. Yeah, why they are feasible in performing the attack and recovering the key. Now, if we do not have any noise, then 80 timing measurements are enough if you are able to very accurately measure the timing. And then, as I explained, you may get average if you have some kind of noise. Now, then what you have to do, we have to make this timing or execution time completely independent. Yeah? Means that independent of the data. It means that it should not matter which kind of pin you enter, always the same time or same long should take till the device answers you. Yeah? It's not easy and it's not as straightforward to do that. Yeah? For example, you may say, that's actually easy. What I can do, for example, I do not return, but I say, hey, I just define something like result, and I put the result actually to true. And then instead of return, what I can do, instead of return, here and here, what I can do, I will say, when I detected the wrong digit, I would say R equals false, and then I return R. No? Then it goes through all 8 digits. But then what happens again, if this is not correct, if this is not correct, then it goes through this. But if it's correct, it doesn't go through this, this instruction. Then this is a pseudocode, or this is something, let's say, high-level code C that you write. What happens in assembly? Yeah, because you have to look at the machine code. Every instruction in the machine code takes different number of clock cycles. Yeah, then you may say, then I don't do it because it goes through this operation and the other one doesn't. Then what I do here, I actually say else, then no. Yeah, no operation. And then if it goes through this, if it's not correct, it does something. If they are correct, then it goes to the knob, and then the number of instructions are actually the same. You don't know, because it's just a high-level program. You have to look at the assembly, and you have to look at the number of clock cycles every instruction takes. No? Only in that case, only if you look at the assembly code and the machine code of the microcontroller, you will be able to say if this implementation is a fixed time or not a fixed time. Yeah? Because fixed time implementation is super important, not for this strcomp or memcomp. It's for entire cryptographic primitives. If you implement something in that we will learn later, that timing attacks are possible. The attacks that they look at the number of clock cycles, which takes one cryptographic primitives to be executed, or cryptographic algorithm to be executed. If this depends on the data, depends on the secret, or depends on the input that you give, it opens the door to perform an attack, to recover the key. Now, suppose that with all of its difficulties, we have done this. We have done this, and we are able to build something like strcomp, which is data independent and it's fixed time. If it's done, the question is whether the attacker still has any chance. The problem is that, yes, even if the time is completely constant, there are still other channels, like let's say side channels, that we can exploit or we can use. And the thing is, most of the digital circuits are based on CMOS technology. I guess you learned something in digital technique about CMOS gates, and they consume energy. They consume energy when they work. And the power consumption of these devices, like the microprocessors, depend on the process data and also the executions, or let's say the instructions. We will see this in more detail later, but then if we assume that the adversary is able to measure the power consumption of the device, how much current it actually takes, or how much power it consumes during this pin checking process, the same attack will be possible. How? Again here, suppose the timing is absolutely constant, everything is perfect, then what happens is that instead of measuring the time for any of these 10 pins that we have, then the power consumption is measured. This is the curve of power consumption during the time that this operation is executed. And the problem is that if the processor performs this R equals false or performs NOP operation, depending on this condition, the power consumption pattern of a device is different. Slightly different, very, very small difference between these power consumption patterns, and this will be actually clear when you compare them. Again, it might be super noisy, and you have not learned how to measure the power consumption yet. You will learn this later. But then it might be also noisy, then you need to repeat this and again measure power consumption, and then, for example, get average and get a clean power consumption signal, and then compare these power consumption curves and see, one of them is different from all the others, and this indicates that all of them went through this R equals false, and one of them went through this NOP operation, and that one identifies that this digit was correct. Now, again, the same attack will work. This is again what I have already explained, that the power consumption traces or power consumption curves will be different, and then you are able to identify one of them as the correct first digit, and you continue this and exact the same situation, noise problem, and the timing information that I have explained for the timing attacks. Now, overcoming this is not easy, as I explained, and the power consumption of device should be somehow independent of the process data, which is actually not happening in the future. And we will, of course, see later how this might be possible and how we can provide security against these kind of attacks. But then the question is, even if you are able to do that, even if you implemented some kind of countermeasure to provide security against this power consumption attack, whether the attacker has any chance to perform this, or perform any kind of other attack to get access to the secure data. Unfortunately, still there are many other kind of attack vectors, and one of them is called fault injection attacks. The problem is that digital circuits like this USB stick or the microcontroller on the USB stick, they need a special conditions to operate correctly. The frequency, I mean, you have learned something in digital technique about the clock. What is the clock? I mean, this is, for example, the clock of your processor. And you heard that, for example, this is the period of the clock, T, and the T should be larger than a particular T, which is called critical path delay. We will talk about this today, but for example, if you have, for example, you buy a mobile phone or you have a laptop, and then you say, okay, the processor is 4 gigahertz. I mean, the 4 gigahertz processor I have, or 2.3 gigahertz. This, what you say about the frequency, I mean, gigahertz is exactly 1 over T, which is the frequency that you have. Of course, if it's higher, for example, it's 4 gigahertz CPU, I mean, if it exists, then it means that this can be shorter, it means that the clock can be faster, and then the device can work faster. What does it mean? It means that the time between these two clock edges, the time which is required for this time is shorter, then you can run it faster. And for every of these, let's say, periods or these cycles, then your CPU performs something. For example, one instruction, or it has instructions which requires 3 clock cycles, and then 3 of them takes 1 instructions to be executed. And then when the clock is faster, then of course more operations or more instructions can be performed by your CPU. Then the clock of your design or your implementation plays an important role on the efficiency. And what is the problem if your processor, for example, is built to work with 2.3 gigahertz, and then you give a 3 gigahertz clock, much faster clock, there is no guarantee that this device actually works. Because, for example, again, digital technique, you learn about milli and more machine, of course, I guess, if you remember. What is it called? I mean, this is a combinational circuit, and this is a register. And the output of the register is given to the combinational circuit, and you have here primary input and primary output taken from somewhere. I mean, directly from the combinational circuit or from the register, and it defines whether you have the milli or more machine. But it doesn't matter. This is a general scheme. All the registers are here. All the registers are here. And this is just the combinational gates, like the AND, OR, XOR gates, and so on. And then the delay of this combinational circuit defines this large T critical path delay. Means that if the clock that you provide for the registers, this is the clock, and this is the clock. If this clock that you provide is faster than T, that's the critical path delay, means that the combinational circuit is not done to provide the output to be stored in the register. Then what happens? Wrong data will be stored in the register, means that the device does not work as you expect. For example, if you have a computer, laptop, or mobile phone, of course, it either crashes directly or it doesn't boot at all. But if the clock is, for example, at the edge, for example, the CPU works with 2.3 gigahertz, and then you slightly increase this speed, then sometimes it's faulty, sometimes it's not faulty. Sometimes it works fine, sometimes it crashes. And this is, for example, one way to inject fault into some electrical devices. The frequency of operation is important, means that there are conditions for the devices to operate correctly, and also temperature. They may work, for example, at maximum at 80 degrees. If you bring them to for example, in an environment which is 100 degrees, what happens? It affects, again, the delay of the combinational circuit. And then if you keep the clock the same as before, then again, the time might be not enough for the combinational circuit to work appropriately. And again, the result might be faulty. And the voltage, you heard about the voltage. I don't know whether VDD is known to you. Every cryptographic device or every electrical device, it has the ground and it has also the VDD, the voltage that you have to provide. And depending on the technology, for example, you heard about, my mobile phone has a processor of 6 nanometer, and before it was, for example, 9 nanometer, and before was 16 nanometer, and then 28 nanometer, and so on, And each of these technologies that you have, which is the size of the transistors, define also the VDD. When you have a super small 6 nanometer technology in the production of your the CPU of your mobile phone, then it means that, for example, the VDD is 0.8 volt. With 16 nanometer is, for example, 1 volt, 28 nanometer is 1.2 volt, and so on. Why it's important? Because when the VDD is lower, then there are some capacitors inside this device, and it takes shorter time for them to be charged and discharged if the VDD is lower. Means that, of course, you can give 0.8 volt to the 28 nanometer technology, a device, but it becomes super slow. You need to give them nominal voltage to work in an appropriate way. Means that you are able to give lower VDD to the 6 nanometer chip, means that it becomes faster because it takes shorter time to charge and discharge the capacitors, and at the same time it consumes less energy. Because of that reason, all the semiconductor companies try to make this technology size smaller. You learn something, you heard something about the size of the technology, and for example, the new mobile phone which comes to the market now uses blah blah technology of 5 nanometer or 4 nanometer or TSMC with 6 nanometer and so on. This is the reason. And then if you change this voltage, then again, the timing information of a device doesn't fit to what you expect. For a short time, you change this VDD from the nominal voltage, 1.2 volt, for example, to 0.8 for a very, very short time. And then what happens for a very short time, you inject fault into your system. The thing is, by this, we intentionally put the device in a situation that it doesn't work correctly. And we call it fault injection attacks. We inject fault into the device, and then we use the faulty outputs to perform the attack and recover the key. For example, here in this example, that's the USB stick and so on. If we inject fault by changing the frequency, clock glitch, or glitch the clock, or voltage glitch for a short time, change the power supply of the chip, what happens in the microcontrollers, usually what happens is that some instructions can be skipped. Instructions, they are executed by the processor, they can be skipped. The reason for that at the moment, be open-minded and accept. We will learn this later, why by fault injection the instructions can be skipped. This is a normal behavior or common behavior of the microprocessors if you inject clock glitch or voltage glitch or power glitch into the microcontrollers. And then imagine that somewhere this strcomp or memcomp is called. And then this instruction which calls this is skipped. Then what happens? The pin checking is completely ignored, and then you may get access to the secure content of the USB stick. The problem of this kind of attack is that every time that you want to get access or skip that instruction, you have to inject the fault. Either you know exactly at which time clock cycle, or which clock cycle you need to inject the fault, or you try a lot of different cases. For example, you inject in the first clock cycle, it doesn't work many times. Injecting the second clock cycle, it doesn't work. Till once it works, and once it works and you get access to the secure data, then that's all. But you got access, but every time that you want to get access again to this content, you have to perform the attack again, or you copy the content once and then you don't want to attack again. These are the things that I explained, the clock glitch and the power glitch, and skipping the instruction is something that is very common, and we will learn this later. Then the attacker doesn't learn the pin actually gets access or pass the authentication process and get access to the secured objects. Now, if you have now some ideas about what the physical attacks are, now, formally they are classified into some groups. From attacker's perspective or attacker's behavior point of view, and also from invasiveness. We have physical attacks that are passive and also physical attacks which are active. Physical attacks which are passive is something like measuring the time, measuring the clock cycle, or measuring the power consumption, as we have seen. Yeah, means that you do not do anything with the device. The device is there, we are just listening to this. Listening to its power consumption, listening to its number of clock cycles required to perform the operation. But the device does not have a chance or much chance to understand and find out that you are measuring its power consumption or counting the number of clock cycles of the device. But some other attacks are active, like injecting the fault. Now, means that you disturb the device, you make some trouble for the device, and it doesn't perform the expected operation. Now, based on that, you classify them into passive and active. But from invasiveness, then we have to actually classify the attacks based on the ability of the adversary. For example, we say the attacks are invasive, means that we do not make any limit for the adversary, any limit at all. The adversary is able to inject faults, to decap the chip completely, and put even the wires into the chip, even make a hole into the device and get, for example, get the signal where the key is stored. Yeah, super a strong attacker model, but they actually classified into invasive attacker models. In the semi-invasive attacks, we say, okay, the attacker is able to open the chip, for example, yeah, but is not able to make any electrical contact. Can actually watch, can shoot some laser, yeah, watch them by some specific devices like photon emissions, and look at the device with some particular cameras and so on. Of course, very sophisticated devices, but is not able to make any electrical contact. And the non-invasive attacks is that the attacker is not able to decap the chip. Yeah? For example, why is important? Because there are some security measures. Some devices have some tamper protection. Means that you open the chip, the device doesn't work anymore. Yeah? I mean, it detects that something happens physically on the device. Then this attack, this non-invasive attack, yeah, of course, this is a relaxed attacker model, is not super strong, yeah, because the attacker, we assume that the attacker is not able to open and the device is not able to understand that, okay, its power consumption is measured, or the device does not have a chance to understand, okay, the clock glitch came in, yeah, because it doesn't need to any decapping. For that reason, then we have 6 different attacks, yeah, with the passive, active, and also invasive, semi-invasive, and non-invasive. And for each of them, I gave you one example. Yeah, for the invasive, that you don't have any limitations, and the device, the attack is passive. You just probe, means that you make a hole into the chip and put a micro probe where the keys are stored, and so on. I mean, you exactly get what the internal values of the cryptographic operations, like the AES. Yeah, in the middle of the AES, somewhere you get some signal out, and then you may be able to recover the key. But if it's invasive, it's also active, then you can force some permanent faults by some electrical contacts. Yeah? This is very a strong attacker model. Yeah? And in the semi-invasive, means that you open it, but you are not able to make any electrical contact. You can do optical inspection by passive. Means that there are some, for example, photon emission. You can when the chips are working by particular cameras, that they are able to detect the photons, you can understand which line of the circuit had some toggles, some changes during the computation, based on the photons which are emitted. Yeah? Or if it's active, then you do some kind of a light attack or laser attack. Yeah, means that you open the chip, you don't make any electrical contact, but you can inject the fault by laser beams, of course, in a super tiny area and some sophisticated devices. If the attack is non-invasive, you do not open the chip, but it's active, it's similar to attacks like clock glitch, power glitch, or changing the temperature. Yeah? But if it's non-invasive and passive, means that the device does not have any chance to understand its power consumption is measured or its timing is measured, and you do not make any manipulation on the device, it's called side channel analysis attacks. Yeah? And if you have heard about side channel attacks, well, side channel analysis attacks actually are physical attacks which are passive and also non-invasive. And it's the most dangerous attacks because it's very hard to detect the attack is being performed. Yeah? And then this is main part of our lecture. We will work here and also a bit here. The rest is not actually covered by the lecture. I just review some basics of the hardware design that you may have learned during your bachelor studies, like the digital technique. But it's just some overview if you require something that you need to learn it by yourself. But just give you some ideas how, for example, the chips are produced. No? If you want to build a chip, you want to build doesn't matter if it's a cryptographic device or not, but then traditionally you divide this process into a specification. You define, okay, what should the device do? High-level description. And also you do some kind of behavioral design, like the RTL. You write HDL code, very like the HDL code of the design. Yeah? And then you do some structural design, means that afterwards the behavioral design is given to some synthesizer, and then the structural design netlist of the transistor or cells are produced. And afterwards this netlist is given to another tool which place and route the entire components that you have in the netlist and then builds the device. Yeah? It means that, okay, where should be every cell and how they should be connected to each other, and then it's given to a fab to fabricate a chip and then send it to you. Huh? And semi-custom design process is based on a standard cell library. What does it mean? Here, when you write VHDL or Verilog, it's just HDL code. It's a behavioral level. You don't know, for example, how the AND gate is implemented, or whether you have 2-input AND gate or you have also 3-input AND gate in your library. Then for making this netlist, through a synthesizer, then you need to give a library to this. And the library says, okay, I have 2-input AND gate, but this is a specification. This its power consumption, this is its timing information, and I have also a 3-input AND gate with this power consumption, with this timing information, and so on. And the synthesizer will have this library and then decide based on the requirement that you have. For example, you say, I want my device to work at 3 gigahertz of the clock. Now the clock should be 3 gigahertz, at least. The fastest. The fastest clock should be 3 gigahertz. And then the synthesizer will try to use the elements of the library to construct the netlist in a way that it fulfills your requirements. Now, then a standard cell library is used for the semi-custom design process. And many things will be done automatically, from behavioral design to the end. And this is called synthesis, what I have explained. And the output of the synthesis is a netlist, and it's actually a graph how these components are connected to each other. When making the layout, when we want to build a chip, ASIC, not the FPGA. Yeah, FPGA is similar to this, but the components of the FPGA are different to the ASIC. It means that this library that you have, which builds the AND gate and so on, in the FPGA are different. Yeah? It means that they are fixed components in the FPGA. And then also there is a tool which says any of these components where should be placed. Because inside the FPGA, the structure is fixed, you just configure them. Suppose that there are some gates that you can change it from AND gate to OR gate, or OR gate to NAND gate and so on, and then the connection between them can be also configured. This is just FPGA. Of course, this is too simple what I explained. The gates are not that small. Usually the gates which are available in FPGAs are larger. They are not 2-input gates. There are, for example, 6-input gates. Super gates are available, and then they can be configured. But in the layout, then the gates or the components should be placed and connected together. Of course, the netlist says how they should be connected, but then The layout says physically and geographically how or where these components are placed. And then the layout is a geometrical description of the design, means that it's not only the netlist, it's also the position of every of these components and how they are connected to each other. And this is the general form taken from the DPA book, with the high-level design, and then you do the synthesis, and then floor planning for the ASIC, and then placement, and then routing. And then at every stage, you should do a verification. And then if you do verification, it doesn't fit to what you want and your requirements, you need to get back and repeat this. Or you see, okay, it doesn't fit at all, it never can reach my, my expectations, then I have to change my high-level description and do resynthesize and so on. There are many checks and verification at every step to finally get one tape out, or let's say chip. And this is one of the chips. This is, for example, again, the banking card, EC-Karte, and this is the contact. And most of the time nowadays, what you do, you use it as a contactless instead of the sticking in the card. But this is the back side. This is the front side, what you see on the card, but this is the back side of the same chip. I mean, this is, and they are actually just the contacts. And the back side, this is the chip. This area is the chip. The rest are they are bonding wires, the wires that are connecting the silicon, which is produced here, to the pins that you have on the top. They are you see 1, 2, 3, 4, 5, 6, 7 pins. And usually, if you look at them, they are either 7 or 8 pins available here, and based on particular protocol, they can communicate. And what we do in the hardware design, this is exactly what we design, this part. The rest is just packaging. And in the contactless communication, the same chip exists, but there are 2 other pins. They are given to one antenna. And this provides the energy for them when they are in the field, and also through that channel, they can also communicate. Then we shortly review AES. Some of you have heard and learned about the AES, that it has 3 different versions, 128-bit, 192, and 256-bit key version. We usually deal with the simplest or smallest version, means that 128-bit version of the AES in the lecture. And the plaintext and the software text are always 128-bit. Then we usually also focus on the encryption function. And then the encryption function is like this, that the plaintext comes in and then add round key, XOR between the round key and the plaintext, and then it goes to the sub-bytes. We will see that, and then to another function which is called shift rows, another function mixed columns, and again add round key, and this is repeated 9 times. This is repeated 9 times. I mean, ignore the first add round key. Afterwards, this is repeated 9 times, and then the last round, the 10th round of the AES 128, doesn't have the mixed columns. Means that add round sub key is there, sub bytes is there, shift rows is there, and an add round key. This mixed column is missing in the last round. That's all. But the thing is, one thing that you may ask, what is the relation between these round keys and the main key? There is a function which receives the key, which is 128, the 128, and then generates these round keys. How many of these round keys we have? 1 of them here, 9 others here, and another one here. Means that in total we have 11 round keys for the AES 128. Now, everything is actually in AES is seen as a 4x4 byte-wise matrix. And most of the things are actually the bitwise operations. For example, the add round key is a bitwise XOR over 2 operands, each of them 128. And then the sub-bytes include 16 SPOXes. A SPOX means substitution box, and each of them is actually just 8-bit function. Means that the input is 8-bit, the output is also 8-bit. Means that you take this 8-bit value from this matrix, you give it to the SPOX, and the output is also 8-bit, you put it here, exactly the same position. We will see later what it is. I mean, the SPOX is an inversion in Galois field 2 to the 8. This is something that we need to learn later in more detail. And it's also followed by an affine transformation. We will also see what the affine transformation means. If you want, you can also search for the AES, and there is an official document by NIST, National Institute of Standard Technology, which is called FIPS. No? They are federal documents. And then you search for the AES and NIST of AES and FIPS, you get exactly the official document, and all the mathematical requirements are also given there with respect to Boolean algebra. And then shift rows is actually just changing the position in their bytes. If you look at here, the first row doesn't change. The second row moves 1 byte to the left. The third row moves 1 byte or shifts one or rotate 1 byte to the left, and the last row 3 bytes. Yeah? This is just changing the position. If you want to implement it in hardware, it's just changing the position in hardware. Yeah? I mean, it's just bit permutation. And the mixed columns receives 1 column, which means 32-bit value, and apply 1 linear operation, and then gives you another 32-bit value. Means that the first column goes to the mixed column and gives you the first column of the output. The second column goes to the exact same function and gives you the second column, and so on. Similar to SBox, which is done the same SBox is used for every byte. Here, the same function is applied on every column individually. Now, the key schedule. I mean, I don't want to go to the details of the key schedule much. You know? Here is 128-bit value. Each of these K is 8-bit again. This is byte-wise operation, because you should keep in your mind that the AES, when it was defined, the AES, which is actually Rindal, the algorithm originally means Rindal, called Rindal, and then it was defined or selected as the AES. It was designed to be efficient for software-based software implementations. And that time, more than 20 years ago, the software-based tiny small microcontrollers were 8-bit microcontrollers. Now nowadays, if you work with like ARM processors, if you have worked, they are 32-bit at least. I mean, it's far away from 20 years ago, but that time 8-bit microcontrollers were common, and even I would say rarely you could find microcontrollers with 16-bit operands 20 years ago. And then it was designed to be efficient for at least 8-bit microcontrollers. And then for that reason, everything is 8-bit, 8-bit, 8-bit. Then you could perform the operations much easier. And the key schedule actually works like this. You have learned something about the Feistel network. This is exactly a Feistel network. Every 4 bytes make a 32-bit value, W0 till W3. And then there is a G function, which actually gets this, and the operation of the G is again 32-bit input, 32-bit output, and then XOR. If you see here, the output of this XOR, the output of this also XOR, XOR, XOR. The only thing that you have is this G function. And the end, this is the first round key, which is 32-bit, 4 times of this W, and each W is 32-bit. And then the next one here, the row, makes you the second round key. And then the same function is applied again and again to generate the next round key. And what is this G function? Again, here is a permutation, just changing the position over the bytes. Means a byte-wise rotation, and then applying the same SBox as you have seen, the same SBox for the sub-bytes. And then there is here XOR with the round constant. I will explain this, which is 8-bit value, and the result is 32-bit. Means that input 32-bit, which was here, the output is also 32-bit. This round constant is just a counter, form of a counter, but it's different for every round. But this is the only thing which is different for the rounds of the AES. If I get back, if you see here, every round is actually the same. Of course, the last round was different by not having the mixed column, but these 9 rounds are exact the same. The only difference is the round key. But the round key is also generated in the same way and absolutely the same, except for the round constant. It means that this is, for example, 1 in the first round, in the second round is 2, in the third round is 4, and so on. It's incremented based on a fashion that we don't deal at the moment. Good. This is what I have already explained. Yeah, these are also round constant. I can explain this in later why it's generated like this. And each round of the key schedule is a bijection, one-to-one function. You know, means that it's reversible. Means that if you know any of these round keys, you can actually compute backwards and get the main key. Yeah? Because the first round key is the main key of the AES of 128. And any of the round keys that you recover, for example, you perform a side channel attack, we will learn later, at the last round of the AES encryption. Then you recover the last round key. From the last round key, you can compute backwards and find out what is the main key of the AES. Yeah? This is what I wanted to explain. Now, how do you implement this in software and also hardware? As I said, in software is super straightforward. The only thing that you need to take care of is the SPOCs. In software, it can be implemented easily by a lookup table, because 8-bit function, 8-bit lookup table, 8-bit input, 8-bit output. Doesn't need that much area, I mean 256 cells you need, and each one has an address of 8-bit. And the mixed column in software is the most expensive operation because there's a lot of XORs that you have to perform. And as I said, it's a linear operation. But in hardware is okay, but in software it needs pretty much, let's say, instructions. But every 4 SPOCs and a mixed column can be also merged to a larger table. I mean, 20 years ago, after AES was being deployed, and then people tried to implement it in a better way or more efficient way, and then the processors became also larger. Means that more memory, more lookup tables were inside, and you could actually mix each 4 SPOCs and 1 mixed column to a larger lookup table, 8-bit to 32-bit, and some XOR operations. And this is implemented or known as a T-table based implementation. That's a T-table implementation. You see here that mixed column receives, of course, because of the shift rows, receive these inputs, and then what you can do, you can have one lookup table, 8-bit to 32-bit, and another 8-bit to 32-bit, and another 8-bit to 32-bit, and so on, and then the results are actually XORed together. Means that it's because it was a linear operation, then you have one lookup table that you use it 4 times, each of them 8-bit to 32-bit, and then the XOR, and the same for this one, the same for the next column and the next column. And this way you can have the AES implemented in software if you have enough memory for these lookup tables. Then with just large lookup tables, which are called T-table, and then some XORs. That's all. Then you can implement entirely the AES. And then pseudocode of the AES, what you can write. X equals the P, plain text, and then XOR with the first round key, and then you have one here loop, 1 to 10. You do sub-bytes, you do shift rows, and if you are not in the last round, you do the mixed column, and always you do also the round key here, and then at the end you have the ciphertext. If you want to implement it in hardware, then you have here plain text XORed with the round key, which is coming from the key schedule, and then there is a loop here, because you want to make the loop, then you need to put the multiplexers, then a SPOCs, shift rows, and mixed column. And then you decide whether you take the output of the mixed column or the input of the mixed column, because here this is the input of the mixed column, and after a mixed column is performed, this is the output of the mixed column, then based on the last round. And then afterwards, you do also XOR with the key schedule, and the output of this is used as a feedback here to work here. Then 10 times you need to do that. You need, of course, a controller which says the start, also says that you are in the last round, and then afterwards the ciphertext will be ready. One question that you may know, I mean, some of you have actually forgotten, you need to put register somewhere because it's a loop. You cannot build this by just combinational loop. You learned actually, again, as I explained, milli or more machine, you need a register in this loop. Either you put one register here, or here, or here, or here, or here, inside the loop, or you put more registers. Because if you put just one register, then for example, the register is here, the critical path delay will be something like this. Will be large and long. Then it takes pretty long to perform one operation or one clock cycle. The critical path delay will be long. Then what you can do, you can put more register inside. Then what happens? Then more clock cycles are required per AES round, but then the clock can be actually faster. And at the same time, if you build a pipeline, then you can give multiple plain texts after each other. If you have 1, 2, 3, 4, and 5 register stages, then you can give actually 5 plain texts after each other consecutively to this. And then when the ciphertext is generated, then 5 ciphertexts are generated also consecutively after each other. This is what I explained. Registers should be placed, but then you can also change this and more optimize it. You can see here the XOR comes to the loop, and if we are not in the last round, then we do some other operations and so on. Then what you can do, this is exactly the same thing. I put a register here, the loop as before. The only difference is that there are not 2 XORs. If you remember, there was 1 XOR here and 1 XOR here. The XOR came to the loop here, and then you do it just once. You can also put the register not only here, you can also put it here, or here, or here, or inside this loop, anywhere that you want, or multiple registers. And the critical path delay, this is something that I already explained to you. If you have multiple registers, then the critical path delay is either here, or here, or here. And the one which is longer, or the longest path, defines the maximum clock period. Maximum clock. And the largest path that you have defines also the maximum clock cycle, clock frequency that you can give to the device. And based on that, actually, as I said, if the clock is faster than this, then you may inject fault into the system. Then one question is here, why in hardware you see here shift rows and mix column are packed? Then we didn't put a register here because shift rows is actually in hardware just routing, just bit permutation. Means that you do not actually perform, it doesn't go through any gate. It has some delay, but it's much, much smaller than having a combinational circuit. And if you have this, which is called actually the round-based implementation, means that every clock cycle you perform 1 round of the AES, means that inside the loop you have only 1 register. And then what happens, then every clock cycle you perform 1 AES round, then in general, in total, 11 clock cycles are enough to perform 1 full AES encryption. If these are interesting, then you can actually have a look at the Moodle course of the other lecture that I give, which is called Cryptography on Hardware. But then you will learn all of this during the lecture, how this can be implemented and how tested, and then the VHDL, Verilog, and so on. Another one that you may do is unrolling, means that you don't put register at all. Everything is combinational. Then you may perform the entire AES encryption in 1 clock cycle, but then the critical path delay is very long, and then you need to wait very long to be able to get the ciphertext out of this. And then this is called unrolling. But then you may say, when unrolling, you see you need also the very much area. I mean, this is super large. I mean, you have 10 times the SBox, 10 times the mixed column, 10 times or 11 times the XOR, and so on. And also the the key schedule also should be implemented. Then what you can do, you can put the register between every round, for example, like this, which is called pipeline unrolling. Now, what happens? I mean, you have the same area as before, even more because you added register. But then what happens? The critical path delay is shorter, and you can run this with a higher speed, and then you can give multiple plain texts after each other every clock cycle. But then you wait 10 clock cycles, but after 10 clock cycles, all the ciphertexts are coming after each other without any delay. Then the same area as the unrolling, but higher frequency. But of course, a bit higher latency. These are what I have already explained. Consider architecture with 10 registers, latency, and how this works. Usually these implementations, pipeline unrolling, are not performed or not used in normal devices. If you want to have a very high throughput, for example, if you have a Cisco router, yeah, and then everything should be super fast, and then the packets are coming, and then with a very, very low delay, then you should have the next packet or encrypted packet ready, and then you can have such kind of implementation. The area is very large, the power consumption is also very large, but it's super fast with respect to the throughput. Very high throughput. Then every 10 clock cycles you have one packet encrypted, for example. But then it's also used for the code breaking. Yeah? You may not have heard this. It's called Copacabana. This is actually, I would say 20 years ago, the device was built to brute force the DES. Yeah? You know the DES was the algorithm was used as a standard before AES, and then of course because the size of the key was short, 56 bits of the key, then you could brute force it. But of course, now at the moment with your PCs, you can do it. I mean, it may take a bit time, but if you have a good PC and also do good programming and also multi-threading programming and so on, you may also check it with your own PC. But many years ago, the PCs were not that fast, and then some FPGA-based code-breaking devices were made, for example, for DES, and the DES was implemented exactly like the pipeline unrolling, because high throughput is required because it searches only for the key. Yeah? One pair of plaintext ciphertext it has and search through all possible keys to find which one actually is a good match. And then the device had 120 FPGAs, and then 8 DES were implemented on every FPGA, and then you can calculate how many DES were running in parallel and then with a very high throughput, and to find the key, for example, in a VIC. Yeah? This is a round-based implementation, as I explained, including the key schedule, because the register is here. The key schedule should also have a register. Then if you remember, the key schedule had also a round constant. The round constant is also coming from one circuit, which increments. Yeah? And then by the start, plaintext is loaded, key is loaded, and 0 is loaded to here. And then, yeah, this works every clock cycle, and then after 11 clock cycles, you have the ciphertext. And you can see the ciphertext is generated from here. This is what I have already explained. T-table-based implementation, you can ignore it at the moment. In the FPGAs, we have some kind of block memories, or large block memories, but they are called BRAM. With the BRAM, we can either implement the SBox only because it's a lookup table, large lookup table, or the T-table-based implementation. It means that 8-bit input, 32-bit output can fit inside one block RAM, and the block RAMs in FPGA usually have true dual port, means that there are 2 ports individually that it can actually work at the same time. Means that you have one lookup table, you have 2 ports with it. One of them means that one lookup table implemented in 2 times at this, 2 times simultaneously is used. Yeah? And then if it's like this, you see here that the T-table-based implementation using BRAM, shift rows is there, and the T-table, and then XORs, and then this concatenation of them, and then bringing back to here. But anyway, what is important, you don't need any register anymore, because the block RAMs have the register inside. Every time that you want to read from the lookup table through the block RAM, what you need to do is to give the clock. Means that 1 clock latency is the minimum, and then you don't need the register at all. Means that similar to the round-based implementation, you can have T-table-based implementation on the FPGA, and it's also clocked, as I said. Now, I mean, I know this is too much information for you, but they are just reference. If we get some other information inside the lecture through the assignments and so on, then when I talk about the FPGA-based BRAM or FPGA-based T-table implementation, then you probably should get back to these slides and review how actually such an implementation may work. There are just information about the last round of the T-table, because the last round is a bit different to the other rounds, because the same XOR cannot be performed. You need to have the SBox output. as I explained, we have dual port, true dual port for the BRAM, and then you need all 16 T tables, and then 8 block RAMs are actually enough for this. The boxes are large in hardware, and then many people try to actually reduce the area, because in hardware at the moment it's not a concern, but many years ago there was a problem. And then the thing is, how can we actually build, for example, a box and use it multiple times instead of instantiating 16 times 1A? Yes, of course, this is super complicated now to be explained, but imagine that you have one box and you have a shift register, then they are actually the state of the cipher, and they are shifted through this box to be stored back into this shift register. Yeah, and this is the key schedule, which is even much more complicated, and I don't expect you to fully understand and follow this, and I don't expect you to actually to do the serialized AES and understand how this works, but you can imagine that every clock cycle, just one box is actually performed. These are just references for you. As I said, if you are interested, you can have a look at cryptography and hardware to see how these implementations can be done.